in calculating the double integral is not as straightforward as evaluating the integral of a single variable calculus. Also, evaluating double integral using limit of Riemann sum is tedious and rarely done. Very fortunate for us that there is a practical method for evaluating the double integral that is based on the general slicing method. And we're going to consider that method in terms of iterative integrals. So for integrative integrals, assume a, b, c, and d are real numbers. We define an iterated integral for the functions f of xy over rectangular regions D equal to AB crossed with CD as there are two forms to this, right? Because the double integral of the functions f of x comma y dA over the domain D. This double integral can be written as the definite integral from a to b, then another definite integral from c to d of the function f of xy. Instead of dA, we're going to say dy dx. So we're going to evaluate the first definite integral with respect to y first, because the limit of integration is between c and d. And then whatever result you get, you're going to use that and evaluate the definite integral from a to b with respect to x. The order on which you integrate matters. So when you want to evaluate the integral with respect to y first, you hold x constant and evaluate the inner integral with respect to y. This gives us a function in terms of x only, and that is you're going to see s of x equal to the integral from c to d of f of x comma y dy. So I'm going to just take the inner part of the double integral and set that equal to s of x. Then whatever result you get from this particular case, we're going to integrate the resultant function s of x with respect to x, and you're going to get the answer. Now similarly, when you consider the case of the double integral of f of x comma y dA over the domain D, and you want to evaluate the double integral with respect to x first and then with respect to y, you're going to see that f of x comma y dx for x going from a to b, and then dy for y going from c to d. So in this case, you hold y constant and evaluate the inner integral with respect to x. This gives us a function in terms of y only. So what I'm going to do is I'm going to take the inner part of the double integral, set that equal to s sub y, and for s sub y is equal to the definite integral from a to b of f of x comma y dx. And then you integrate the resultant function s sub y with respect to y, and you're going to get the final results. Okay, so let's take a look at the following example. In this example, you want to evaluate the integral from 0 to 1 and integral from 0 to 2 of the function 6 minus 2x minus y dy dx, and you're going to perform the same calculations but with the x first and then dy. So follow the iterated integrals approach earlier. When you want to evaluate the integral with dy first and then dx, what you do is you hold x constant, or you fix the value of x. So in this case, you have the function z equal to 6 minus 2x minus y, and this is the plane of considerations, or the function of considerations. And you want to find the side volume of the solid regions bounded by this plane, and the rectangular regions in the xy plane where x is between 0 and 1 and y is between 0 and 2. Now, if you want to evaluate the integral with respect to y first and then with respect to x, we follow the approach of iterative integral. That is, we're going to hold x constant and evaluate the inner integral with respect to y. Or, you see in the purple here, this is a line at a fixed value of x. And this line has the area a of x, where x is between 0 and 1. So I'm going to perform that calculation. So the integral from 0 to 1, then integral from 0 to 2 of 6 minus 2x minus y dy dx. And if you evaluate the inner integral first, you're going to get a function in terms of x only. So the inner integral is just the regular integral that you see already in single variable calculus. When you evaluate this integral with respect to y, you treat x as a constant, or you hold x as a constant. So that is, this is equal to the integral from 0 to 1 of the integral of 6, or antiderivative of 6 with respect to y is 6y minus 2x. Again, in this context, x is a constant, so negative 2x is a constant. So the antiderivative of a constant with respect to y give you negative 2xy. And then you find the antiderivative of y, that is 1/2 y squared, so minus 1/2 y squared. And then you evaluate this function you just found at 0 and 2. dx, because you still have the outside integral to take care of later. So evaluate this function as 2 and 0. You're going to get integral from 0 to 1 of 6 times 2 minus 0 minus 2x times 2 minus 0 minus 1/2 times 2 square minus 0 square dx. So this is equal to the integral from 0 to 1 of 12 minus 4x minus 2 dx, or the integral from 0 to 1 of 10 minus 4x dx. Now at this point you can see that when evaluate the integral with respect to y first, or the inside integral, you get the function in terms of x only. And at this point you can evaluate this function with respect to x for x going from 0 to 1. So here you get 10x minus 4 times x squared over 2, evaluate at 0 and 1. Or you simplify this a little bit and you get 10x minus 2x squared, evaluate at 0 and 1. And you get 10 times 1 minus 0 minus 2 times 1 squared minus 0 squared. And the result should be 8. So now that's one way to do it. A different way to do it is to evaluate the integral with respect to x first and then with respect to y. When that is the case, you see here you have a slide at a fixed value of y, and the slide has the area of capital A sub y, where y is between 0 and 2. That is, you're going to evaluate the integral with respect to x first. That is, you're going to get the area of this slide. Whatever area you get, you evaluate that area with respect to y, and then you get the answer. So in this case, I want to note that this is a slide as a fixed value. Y has area capital A y, where y is between 0 and 2. Alright, so we're going to use this integral to evaluate the sine volume. Okay, so again, what you do is you evaluate the inner integral first and then the outer integral. Here's what you got. So the integral from 0 to 2, the integral from 0 to 1 of 6 minus 2x minus y dx dy. In this case, you're going to hold y constant, or you treat y as a constant, and evaluate the integral with respect to x. So you got the integral from 0 to 2 of the inner integral. So the antiderivative of 6 with respect to x gives you 6x. The antiderivative of x is x squared over 2, or you have negative 2 times x squared over 2. And in this context, y is a constant, so the antiderivative of y with respect to x is negative xy. And you're going to evaluate the integral at 0 and 1 dy. So the integral becomes the integral from 0 to 2 of 6 times 1 minus 0 minus 1 square minus 0 square. So this 2 and this 2 cancel out already. Minus 1 minus 0 times y dy. So you get the integral from 0 to 2 of 6 minus 1 minus y dy. And as you can see, the function you just obtained is the function in terms of y only. And we're going to evaluate this function with respect to y for y going from 0 to 2. Here you get the integral from 0 to 2 of 5 minus y dy, or 5y minus 1/2 y squared. Evaluate at 0 and 2. You get 5 times 2 minus 0 minus 1/2 times 2 squared minus 0 squared. You're going to get 10 minus 2, and that is equal to 8 as well. So for the double integral, no matter what the order of integrations, you should get the same answer. So the question is, why even bother to switch the order of integrations when no matter what order you have, the answer should be the same? When you get to the more general regions of considerations, or the more general domain, sometimes it's a little bit easier to evaluate the integral with respect to x first and then with respect to y. Or sometimes it's easier to evaluate the double integral with respect to y first and then with respect to x. That is the reason we want to switch the order of integrations depending on the function of consideration and the general regions of considerations. And you will see that later in the next lecture. In the next example, we're going to evaluate the double integral with just the suggested order of integrations. So in this case, you could like to integrate the functions with respect to y first and then with respect to x. So we're going to evaluate the inner integral as follows. So it's equal to the integral from 2 to 4 of. So when you evaluate the integral with respect to y first, x is a constant, so e to the x is also a constant. So you can pull e to the x out of the integral operations and just evaluate the integral from 1 to 9 of y dy, and then with the x. So the antiderivative of y is 1 half y squared. Here you get the integral from 2 to 4 of e to the x times 1 half y squared, evaluate at 1, 9 dx. So the integral now is equal to the integral from 2 to 4 of e to the x times 1 half of 9 squared minus 1 squared dx. And if you evaluate this expression, we're going to get 40. And you can pull 40 out of the integral operations to get 40 times the integral from 2 to 4 of e to the x dx. And the antiderivative of e to the x is just e to the x, so you get 40 times e to the x, evaluate at 2 and 4. So you have 40 times e to the 4 minus e squared. Example 3, you could like to compute the double integral of the function with respect to the rectangular regions of x between 0 and 2 and y is between 0 and 1 for f of x comma y is equal to x. In the last example, we already evaluated the functions with respect to y first and then with respect to x. In this example, because there's no indications of what order we should follow, I'm going to evaluate the integral with respect to x first and then with respect to y. So the setup of the double integral is the double integral of x dx dy for x going from 0 to 2 and y going from 0 to 1. Now, the antiderivative of the function with respect to x is going to be 1 half x squared. You get the integral from 0 to 1 of 1 half x squared, evaluate at 0 and 2 dy. And here you evaluate the functions, you get 1 half times 2 squared minus 0 squared dy, or 2 squared is 4 minus 0 is still 4 divided by 2 is 2. You get the integral from 0 to 1 of 2 dy, or this is 2y, evaluate at 0 and 1, or this is 2 for that matter. We're going to move on to the next example. In this example, you also want to evaluate the double integral of xy minus 3xy squared over the rectangular regions of x between 0 and 2 and y between 1 and 2. So here I'm going to evaluate the double integral with respect to x first. So the setup is double integral of xy minus 3x times y squared dx dy for x running from 0 to 2 and y going from 1 to 2. Because we evaluate the inner integral first with respect to x, what you do is you treat y as a constant, and you get the integral from 1 to 2 of 1 half x squared times y minus 3 times 1 half x squared times y squared dy. Now you're going to evaluate the function at 0 and 2, and you get the integral from 1 to 2 of 1 half times 2 squared minus 0 squared times y minus 3 half of 2 squared minus 0 squared times y squared dy. Do a quick calculations. We're going to see that the integral becomes the integral from 1 to 2 of 2y minus 6y squared dy. So this function is the function of y only, and we're going to integrate this function with respect to y. So you get 2 times 1 half y squared minus 6 times 1/3 y cubed, and we're going to evaluate this as 1 and 2. So simplified calculation, we get y squared minus 2 times y cubed, evaluate at 1 and 2, and you get 2 squared minus 1 squared minus 2 times 2 cubed minus 1 cubed, and this is equal to negative 11. So again, the volume is always going to be positive. You get a negative value in this case because what we are calculating is the sign volume of the solid regions. All right, so let's move on to the last example in this lecture. We want to calculate the double integral of e to the x times cosine of y dy dx. So we want to evaluate the functions with respect to y first and then with respect to x. So you're going to see the integral from 0 to 2 of e to the x times sine of y, evaluate at 0 and 2 pi over 2 dx. So again, in this context, x is a constant, so e to the x is also a constant. You can pull that out of the integral operation and just integrate cosine of y with respect to y, and you get sine of y for that matter. Now evaluate sine of y at 0 and pi over 2. You're going to get the integral from 0 to 2 of e to the x times sine of pi over 2 minus sine of 0 dx. So sine of pi over 2 is 1, sine of 0 is 0. You're left with the integral from 0 to 2 of e to the x dx. And antiderivative of e to the x is just e to the x. We're going to evaluate this as 0 and 2, or e squared minus e to the 0, or e squared minus 1. And so that's it for me, and that's it for this lecture. In this lecture, we look at the double integrals of rectangular regions. And the idea of double integral is to evaluate the sine volume of the solid regions bounded by the curve z equal to f of xy and the domain in the xy plane. So that's it for me. Please let me know if you have any questions. Thank you.